Hey everybody, this is part 4 in my ESR Shield for the Arduino Uno series. Um, in this video we're going to be going through the code that's making all this magic happen on the Arduino. What you see here, I have this set up in Atmel Studio right now with the Visual Micro plug-in. If you guys haven't seen that yet, I suggest you guys go ahead and check out those other videos. I have a link down in the description. It's a great little add-in that allows you to program your Arduinos in the Atmel Studio, and also has one heck of a great little debugger with it. I uploaded the INO file. It's in my Google Docs folder. There'll be a link in the description down below. I didn't upload the entire project. I just uploaded the INO file, so you can be compiled with just a general standard Arduino IDE, or you can. I suggest you go ahead and get the Atmel Studio 6.1 and install this Visual Micro plugin. It gives you IntelliSense, like I said, the debugger. It's all the bells and whistles of Visual Studio, all thrown in for the Arduino platform. And the best part about it, it's all free. You can download Atmel Studio 6.1 free. You can download the Visual Micro. That's free. And there's a 30-day trial on the debugger. The debugger, there is a small charge for it right now. It's going for $15, but it's well worth it. So anyway, you've seen the other videos. I'm using Arduino Uno R3, my homemade Arduino Uno Shield, and then that SainSmart LCD. The LCD really is optional. You can run this directly out of the computer through a serial port instead of the LCD. All you need to do is go through and change the LCD print line statements to a serial print line statement, and initialize your serial communication, and you're done. So however you wish to build it, you could even breadboard the Arduino Shield if you wanted to. There's really however you want to go about it. To start with, this is just a header of my code. You can see the text color of the comments in the Atmel Studio screen, and then you have your reserved words in blue. You go all the way through here. It's almost 400 lines of code, so it's a pretty short little program. It wasn't too hard at all to build. So I just want to go through and I'll read these comments so you understand it. And if you have any questions at all, don't be afraid to ask them down in the comment section, okay? Because I want everybody to understand exactly what's going on with this. Otherwise, you may not be able to troubleshoot it if you have issues. Anyway, the ESR code, what we're doing here is we're reading an analog input on pin 5. It converts it to an equivalent series resistance measured in ohms. We print the results to the LCD or your serial port, whichever version you want to use. And to be used with the ESR Shield Rev 1 and the Arduino Uno R3. And we're going to set the Arduino Uno ADC to use the 1.1 volt internal reference. This just gives us the Arduino Uno has a 10-bit ADC, and when we set it to the 1.1 internal reference, that gives us a millivolt resolution. And that's important that we have that in our measurement, especially with the low ohm that we're going to encounter with the measurement of the resistance in the capacitors. Okay, the pins we're using on the Arduino is the analog pin 0. It's used by our SainSmart LCD buttons. Since we're using the 1.1 internal reference for A5, measuring the resistance through the or measuring the voltage drop across the capacitor, the only buttons that are going to work are the up, down, and right buttons. The SainSmart Shield was set up to use the 5-volt reference on the ADC. A5 is used to read the rectified voltage output by the second stage of the op-amp on the Shield. The D2 pin, the digital pin 2, is assigned an external interrupt. This method sets a flag to display the calibration detail on the LCD, and you can also set it up in code if you don't have a button shield on your LCD. You can use this button to also toggle the calibration factors also. The ESR Shield must manually be spanned using trim pots R9 and R5 such that the output of the ESR pin A5 reads during calibration. With the leads shorted, we need it to read around 700 millivolts, well, at 700 millivolts. And when there's a 10 ohm resistor connected across the leads, we need to dial it into 295 millivolts. I did a video on the setup and calibration of the shield, so I'm not going to go into too much detail. Let's put this calibration procedure into the code just for completeness. The calibration is documented in a video. You need to see that to kind of go along with this. But anyway, the procedure is to remove the LCD shield if it's installed. Then we want to center the trim pots R5, R6, and R9, the attenuation, the frequency, and the load pots. And then first we set the frequency. With the ESR Shield installed on the Arduino and the Arduino powered up, we need to connect your multimeter. When it's set to frequency, or you have a frequency counter, or even an oscilloscope, we set that to pin 1 of the op amp. Pin 1 of the op amp is the output of the oscillator. We have it set up as a comparator oscillator on that first stage of the op amp. And then we adjust the ESR Shield trim pot R6, the frequency pot, to set the desired frequency, and that's typically 100 kilohertz. But you can set it to whichever frequency you wish. In the next revision of this, we're going to be able to change the frequency on the fly through the Arduino software by using a timer comparator inside of the Arduino. I should be able to set up a frequency span that's selectable from practically nothing all the way up to about a megahertz or so, or 8 megahertz I guess it was that I've tested. When we get up to higher frequencies, the loss in the transformer becomes pretty significant, so you may not be able to use anything more than about 1 megahertz, but it's rarely used at that high anyway. The voltage output calibration is as we just short the test leads, and then using the voltmeter, we'd hook the voltmeter up to analog pin 5 and the ground pin on the shield, and we adjust the trim pot R9 until the voltmeter reads 700 millivolts. And we remove the test leads, and we put a 10 ohm resistor across them, and we adjust trim pot R5 until the voltmeter reads 295 ohms. And we just repeat that procedure. Again, I would just refer you back to the video where I demonstrated this until we get stable readings at 700 millivolts and 295 millivolts. It doesn't have to be absolutely perfect. Just get as close as you can. Then we go ahead and connect the LCD shield back up again, and we're ready to go. Okay, the header of the program starts where we're including the library for the liquid crystal display. On the Sane Smart, we have the LCD pins RSEN, the enable pin, and then the data lines 4 through 7. So we're just creating an instance of the LCD class and naming it LCD. And this is the pin Sane Smart LCD. I'm having a little bit of trouble here with my computer's not cooperating. Anyway, again, it's on the Sane Smart, you have your RS pin at 8, digital pin 8, the enable pin's 9, and then the data lines 4 through 7. The ESR Shields using analog pin 5 to measure the voltage that we're going to derive the resistance from. And we're just setting up our constants here for ESR pin is equal to analog 5. Analog pin 0 again is used by the LCD buttons. So those are our calibration pins. Whenever a button is pressed on typically the up button on the LCD Shield, the user is requesting a calibration, so it's pin A0, analog 0. Then we have the constant noise floor, and what this is doing is it's setting a limit for the program to ignore any value of 50 millivolts or less as just noise. And that's just going to tell it to throw it into the open loop output. We have the show cal val pin, show calibration value pin. This is the pin on the shield. It's a digital. It's connected to the digital pin 2, and when this button's pressed, it means that the user is requesting to see the calibration factors. The constant voltage, the voltage step. This is how you fine-tune your ADC on your Arduino. During the calibration factors, we use the multimeter to set the span on the meter at 700 millivolts. And once you get it all done and get your display back up and running, we want to set this up and change your voltage step so that when your ADC is reading 680 millivolts, so we want it to read 700 millivolts, and this is the factor that we use to change in order to calibrate that ADC. Just the ADC val, that's just the value we're going to use to hold the ADC. The ADC temp is just an unsigned long value that we're going to use to accumulate the ADC value. So we're going to oversample the value by, or the measure, we're going to oversample the measurement by 64 times, and then take the mean average of it. Variable to float voltage, obviously, is just a value we're going to use to hold the voltage in measurement. That's calculated by the ADC. Variable to hold a calculated resistance measurements from the ADC line. That's just our ohms. This is going to be determined by the ADC value later on in a little function. Variable to hold the ADC calibration factor. This is when we throw it into a calibration mode, it's going to determine how far it's out, and it's going to store the calibration factor in this variable. The interrupt variable used to signal the calibration function is requested, so when the user presses the button on the shield, it's going to set this flag, and then we're going to down below here the show cal flag is this is the interrupt variable used to tell the program, the main loop, that the user wants to see the calibration values. And then the show cal is just what we're going to use to toggle the display of the calibration factors inside the main loop. I kind of isolated, you're going to see these volatile, these are used by our interrupt programs. And what I did was I just set these up as flags so that I'm not actually changing anything inside the main loop of the program. It's going in there, it's flipping a switch and jumping right back out of the interrupt again. And that's the best way to handle these interrupts on these little microcontrollers. Just set a flag, jump out, and then pull inside your main program to see if you've had any user interaction. That also helps with the bouncing too, is because you don't have to worry about your switch bouncing up and down a couple times and then throwing it into a loop and having to have Schmidt triggers and everything else on your board. Usually, if you just set a flag in the main loop, you can get by with just putting a small value capacitor across a switch to ground and pulling the pin up high. And that's what I did on the shield. Moving on anyway, down below we have a table of values, and these were just values that I measured with the ADC when the shield was calibrated. It spanned from 700 millivolts to 295, and these are the known values of the resistance. I guess I should go into a little bit about the theory behind this. I need to pull up my EagleCAD files, and we'll kind of talk about why I just can't use Ohm's law. Well, I could, but what we set up inside of on a shield was it's not a straight because I had that attenuation pot on the test lead. What we're actually sending into the op amp to be amplified is a voltage divider. And let me pull my EagleCAD files and then we'll talk about that. Okay, I got the EagleCAD schematic loaded now for the ESR Shield, and I can talk about a little bit what's going on here with our measurement. Again, we're getting putting out a 5-volt square wave going through our transformer, and we're knocking that down, so we're getting about 170 millivolts on my design anyway, roughly 170 millivolts peak-to-peak output signal. We have a 10 ohm resistor to ground here, and let's just grab any of the transient spikes that may occur inside our transformer. So we have 170 millivolts nominal coming across our test leads. And then coming down, it's being decoupled by our 10 mic cap, and then going through a 1K resistor into the inverting input of our second op amp, where it's being amplified and rectified out to our meter. Then we have another little pot here. This is our spanning pot here, load pot on the op amp to stabilize the rectified voltage. Then we have R5 here. Then what this is doing, this is attenuating the output of the probes. So what we're basically doing is we're setting up a voltage divider here. We have a constant voltage coming off our test lead 1, and then our device under test, our capacitor, is coming across T1 and T2 here, and we're getting a voltage drop. So this is acting basically as a resistor, and that's what we're measuring, is the resistance across that capacitor. The voltage drop across here is coming down and being attenuated by R5, our pot. So what we're basically setting up, we have our two resistors. This is R1 and this is R2, and the output is going into our op amp as a signal to be amplified and rectified and measured. So what we have is just a basic voltage divider. And with this one being an AC signal, so we'd have to calculate the RMS of that signal, and then this value at R5 is unknown. I mean, we've tuned this down, and we've never measured it. It's just laying there, attenuating the signal of the probe, so that when we have 10 ohms across this point here, the output of the signal will be equivalent to 295 millivolts, and that's accomplished by attenuating this, turning this pot to attenuating that signal. So as you can see, the formula for our voltage divider is R2 divided by R1 plus R2. It makes it a mathematical nightmare trying to calculate the resistance between test leads 1 and 2. So the easiest way to do it is just to plot the actual voltage drop physically, and then using the map function inside of the program to interpolate those values in 1 ohm steps. And that's the reason I did it this way, and that's why you're going to see that resistance table there. And I just want to throw that out there so everybody understands exactly what was going on with this program. And again, if you have any questions, don't be afraid to ask. I'll take time and explain this. It's important you understand the theory behind this so you can you'll be able to troubleshoot it. Okay, so back into Atmel Studio now, and these values you see here, the constant float values, are the ADC values of the different resistors that I measured. And this is just a table down that I created so we can interpolate the resistance by the ADC values. You'll see down below in our ESR calc where I go through and use a map function. And basically what we're doing, we're just setting up a slope for the voltage drop across that resistor, and then calculating the resistance by the drop in the voltage across there by using the ADC values. It's a slope function, basically all it is. Okay, so we're in our setup routine. This is initialize our LCD 16 lines by 2. We're going ahead and setting up the analog pin 0 as our cal pin. This is the pin on our LCD shield. Then we're going ahead and setting the pin high so we can use that pull up resistor. We're going to call the initialize the pin change interrupt, and this polling, we're setting this up as a PC int 1 on our analog ports, and let me jump down below and explain this function one and why we're calling it here. This method here is we're just calling it once out of our setup routine, and it's the only time it's going to be called in our program. It initializes, like I said, the pin change interrupt, the ESR PCInt 1. And we'll use this polling method to detect when the SainSmart LCD shield button is pressed. They're connected to analog pin 0, and when pressed, they pull down the voltage on analog pin 0. So by connecting the other side of the switch to ground to the resistor, then we can then identify the voltage read on analog pin 0. But since we're using a 1.1 volt reference on the ADC to measure the resistance on these capacitors, this kind of limits our the number of buttons that can be read. So with my design here currently, that we can only read the up, down, and right buttons, and any of these buttons can be used. It'll fire the same event. And going into this from our setup routine, again, we're just going to clear all the interrupts. Then we're going to enable the PC int interrupt. Set the mask for that interrupt pin, and we're setting up the only to pay attention to the analog pin 0, and then we just turn the interrupts back on. Okay, and then down below it's this analog reference, setting it to internal. I didn't do a lot of research on it. I don't know if this will work on a Megas or not. You really, if you're going to use this for another board, you really need to check and see exactly what the if it does have a 1.1 internal reference or not. But anyway, this is how we set up our 1.1 volt reference on the Uno for the ADC. Then we're going to go down here and set the pin mode as an input for our show calibration pin. That's the pin on the Arduino Shield that's connected to digital pin 2. Set it up as an input. Then we're going to go ahead and use digital right to set it high. And then we're going to go ahead and use the attach interrupt method to attach the shield button on pin 2 to fire, and call this interrupt shield ESR shield button function on the falling edge of that pin. So this function here is going to be called each time the user presses pin 2 and the voltage on that pin drops. It's going to be detected by this interrupt. Let me drop down to that function. I'll show you. I put all my interrupts down here on the end because once I've written, they're real simple. All we're going to do is we're going to go in there, and this is it right here. Both interrupts are the same. All we're going to do is set the flag. When that pin's pressed, the processor detects that the voltage on that pin is dropped, and then we're going to go through. It's going to call this interrupt. It returns nothing. It takes nothing in as a parameter. It's going to go in here, and it doesn't care what the previous state of that show cal flag, that volatile Boolean value that I had set up as a variable. It's just going to set it true, and then right back out. So, and that's the best way to run your interrupts, just as short and sweet as possible. Set a flag and jump back out. Okay, so just to recap here on our setup on our interrupts, we're working with two interrupts basically. We're using the PC int 1 and the PC int 0. The first one, the pin change interrupt on our analog pin, we're actually calling that down through the actual interrupt register. We have our I want to go over this once again. Is this the initialize our LCD button interrupt, and this is again the interrupt on our button shield, and they're both located down here. I suppose I should fold this code up. The nice thing about Atmel Studio is you can fold all this up and get it out of your way. But anyway, these are two interrupts. This INIT LCD button interrupt, this just goes through and sets up the interrupt. Then what will happen is this interrupt is setting up our PC and our ISR interrupt service routine for the interrupt 1, and every time that button gets pressed or that pin falls low, it's going to call this ISR down here, and it's doing the same thing basically as our other one was. It's just setting a flag. We're going to go in here. If that button on that shield is pressed and it's sensing the change on the analog 0 pin, and that's just set here. You can set it for analog 1, 2, 3, 4, 5, etc. just by setting these different bit values. So it's sensing that change in that pin. When it hits it, we're coming in here. We're just setting that flag true. We're not testing any condition. We're just setting the flag true and back out. And really, we don't care if that bounces or not. If it does bounce, all it's going to do is set that true flag again. The same with this pin on our shield, pin 2, that it gets set true, the show calibration flag, and we're right back out of it. Okay, that pretty much goes over all our setup. Functions, variables, and just getting everything up off the ground. And next we're going to go into the main loop of the program. Let me go ahead and roll this code that we've already talked about. We'll roll it up, get it out of the way. You can see it still leaves the title of the procedure, function, the method there. Okay, we've already gone over the purpose of the code. This is our constants, so we can't roll those up, but go ahead and roll up our setup. Okay, so now we're down into the main loop of the program. The purpose of the main loop is this is where all the work is done. That it comes through, it's going to check the cal flag each time through, and it calls, if the cal flag is set, it's going to call a calibration routine. Next, it's going to check the show flag, the show cal flag, and that's going to toggle on and off the display of the calibration values if the users requested it. We're then going to read 64 samples of the ADC on analog pin 5 at a 1.1 voltage reference. Then we're going to calculate the mean value of the ADC and determine the voltage. Then we're going to call the ESR calc function, where we're going to interpolate the resistance from the ADC value. Okay, so first off, as I said, we're going to go in here and we're going to see if the user pressed the calibration flag. The calibration flag again is on the button shield. If the flag has been set by the interrupt routine, we're going to go ahead and call this calibrate function. The calibrate function is just right down here. The purpose is we're going to calibrate the ADC by reading it 64 samples, averaging them, and then subtracting the measured value from 680, which is the target ADC value that we set up in the calibration of the potentiometers. And this is the ADC is 680. ADC is equal to 0 resistance. So again, we need to short the test leads together. We just have a temporary, or we have an unsigned int, the ADC val, an unsigned long, the temp ADC val, which is we're going to use it to store the ADC values in the for loop. We're going to clear the LCD. Then we're going to print calibrating, so telling the user that we're in the calibration routine. And we just got a little for loop here. It's going to run through it 64 times. And then the ADC value is going to be assigned by the analog read, the ESR pin. Then we're going to store that value in the temp ADC value. So we're just taking with the value read and we're going to be adding it to the previous temp val, and then we're just going to loop through. We're going to delay 5 milliseconds there just to stabilize the it reduces the flicker on the LCD display, and it lets the ADC settle and recover. It helps reduce the noise on the ADC. Okay, so then after we've gone through this loop 64 times, this temp ADC value, we're going to shift its value right. That's the same as dividing it by 64, so what we're going to end up with is an average. The ADC valve is going to have the average of that 64 samples. Excuse me. So then our ADC correction factor is simply going to equal 680 minus whatever that mean value was. Then we're just going to delay 500 milliseconds just to allow the user to see that calibration message on the text on the LCD, and then we're going to clear the display so we can resume with the normal values. So pretty simple, straightforward. It's pretty much the same as the ESR calc, or the calculation we use to determine the ADC value in the main program. But this is just set off to the side, and we're going to assign the AD correction factor by the difference of those two values. This correction factor can be either positive or negative. If the average ADC value is higher than 680, then obviously we're going to have a negative number here as our ADC correction factor. Okay, calibrate function is done now. And then after the calibration function returns, we're going to set that calibration flag false and reset that interrupt flag. And that's why when you're just setting flags like this, that you really don't have to worry too much about debouncing them and have to have Schmidt triggers and all this stuff. It's because we're setting the flag, and it doesn't really matter what's happening. It's we're inside that calibrate routine, and so it's running through it, and that switch bounce is only going to last for 100 milliseconds maybe at the most. I could take a picture on my oscilloscope and post it too if you guys like to see the actual bounce on the switch, or you can Google it too. There's plenty of good examples out there, but this is going to deaden it. I'm not going to have any trouble with the switch bouncing and calling that interrupt routine a couple different times. See, if we'd put this calibrate function inside a calibrate inside that interrupt routine, then we may have been calling that calibrate function several times before that switch settled down. And the same thing with our show cal flag. The user pressed the button on the shield to request the display of the calibration factors, and all we're going to do here is we have this Boolean value that we're just going to toggle back and forth on and off with this little tilde symbol. That's what that's going to do. Just if this it's going to return the opposite. So if this is set true, then it's going to be false. Then what we're going to do is the show cal flag is we're going to go ahead and turn it back off again and clear the LCD. We're clearing the LCD here, so if the calibration factors were previously displayed, it will erase the display so they're not seen anymore. Okay, so down here we're just going to clear our temporary ADC value and set it to 0 before we go into the for loop. And this for loop is just like the other previous one in the calibration routine, where we're just going to have an analog read on our ESR pin and store that value in the ADC val. Then what we're going to do, we're going to add it to the ADC temp and then assign ADC temp that new value. Delay 5 seconds to allow the ADC to settle a little bit. And then after 64 times through that for loop, we're going to come back out, and then again we're going to shift that value to the right 6 places, which is equivalent of dividing it by 64, and this will give us our average value of the ADC. If the resulting ADC value is above the noise floor, then we're going to go ahead and apply the correction factor to it. So if we got a little conditional statement here, if our ADC value, or the mean ADC value, is greater than a noise floor, the noise floor in my code here is set at 50, then what we do is we go ahead and add the ADC value plus our correction factor. Okay, then we calculate the voltage measurement from the ADC value. The 10-bit ADC has 1023 steps relative to the 1.1 volt reference. But you also have to remember that I had that voltage step that I fine-tuned this value by. Mine I tuned in at 00103 is where it ended up matching my multimeters at. So yours may vary a little bit. This is just a good starting spot for you guys to use as a number to get started with, and you can fine-tune that voltage step constant up above and actually get the voltage. And the voltage really isn't used for anything other than just to see exactly where you're at on the ADC. So if you have a correction factor gets too wildly out of hand, you may have to go back and respan your meters. I never have yet, but it's there if we need to. The ESR calc function, this is where we go down and we actually determine the resistance by the ADC value, and we'll jump down to it. As you can see, the ESR calc function, it returns a float and takes an unsigned integer as a parameter, which is called ADC. And we go down here and we're just using if-else statements down through here, so we get a range of values. So if our ADC value is greater than 621, then we know that we're working with a resistance that's 1 ohm or less. And then what we do is we map these values, that whatever the ADC value is, we're going to plot it and determine what the slope is from 0 to 1 ohms, and then plot that value in that slope and return it as a floating point number. And we just go down through this list one at a time, through 1 ohm to 2 ohm to 2 ohm to 3 ohm, etc., 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 all the way down here. So we have 1 ohm slopes that we're plotting in there on that ADC, and that's how we can get the accuracy. So I mean that's really simple. And then down at the bottom we just got the catch that it's going to take it all the way down from 20 ohms all the way down to the noise floor. Now it's only set from 20 to 21 ohms, but it's not constrained. The map function doesn't constrain the limits of the ADC value. So if you have an ADC value that is outside of the 21 ohm limit, it's still going to calculate the value in that slope. It's just probably not going to be very accurate. And anything more than 20 ohms, it really doesn't matter anyway. Most of the time, we're going to be looking with the ESR and these capacitors that are going to be, gosh, a couple ohms or less. Unless they're bad, and then it's going to be easy to tell they're bad. Okay, so we're done with that function. And so go back up to where we called it at. Is ohms is this, so we're returning that floating point value out of that function. And now we're just going to throw it out and display it on the cursor. And these are the LCD commands. And if you don't have an LCD, you can just run it through your serial port back in your computer and just use a serial print line statement. We're just going to set the cursor at the home position 0, 0, and then we're just going to print the ESR label. Then we're going to move the cursor back to the fourth column. And if the ADC value is greater than a noise floor, we're going to go ahead and print that return value from our ESR calc, the ohms value. And then inside the LCD ROM, there's actually an omega character that's stored there, and this is the hex number of the character. So we're just going to go ahead and print that out behind the number value. We're going to print it with 2 decimal precision right here. And if the ADC value is not greater than a noise floor, then we're just going to print the OL for the open loop. And down below is if the show cal flag is set, then we're going to go ahead and display the calibration factors. And there's self-evident what I'm doing here, and I have it commented. And then we're going to delay 50 seconds just to let the LCD processor catch up with all the statements that we've written to it. And if we don't have this, the display tends to flicker a bit because we're running through this loop quite quickly. I'm not sure what the update speed is, but it's fast. It'll make your display flicker if not. So that's pretty much the end of that, the main loop of the program. And then this map function I have here, it's the same as the standard Arduino map function. It's just the map F, where I've been, instead of using long values, I've just changed all the variables to floats for the ohms slope mapping. So anyway, that's everything in a nutshell right there. I mean, it's pretty simple, straightforward. I really don't have anything else to say. If you guys have any questions, make sure you shout out and leave a comment down below, and I'll be more than glad to answer your questions. But other than that, it's a straightforward program. I'll have, like I said, I'll have a link to my INO file that's on my Google Docs folder down below in the description, and go ahead and check out that Atmel Studio with that Visual Micro plugin that I've got running here. Yeah, it's really a wonderful thing. And thanks for watching.